We're going to go over some problems of measuring heights and calculating the pressures based off of barometers. This is our first very popular exam problem right here. Calculate the height of a water barometer at 100 kilopascals, 20 degrees Celsius, and we're given the density of water right here. So we have this water barometer, and we want to know the height of the water in the column. Well, we're going to start off with our equation that we just derived. P equals rho hg. This is our pressure for the hydrostatic pressure. From here, we'll solve for h. We'll divide both sides by rho g and then just flip the equation. And at this point, we can basically plug things in. We just want things in terms of SI units. So our density, 0.9972, is in grams per centimeters cubed. We want it in kilograms per meter cubed to be in SI units. So we'll multiply this by 1 kilogram for every 1,000 grams, so that grams cancel out. And then there's 100 centimeters for every 1 meter, although we need to cube this fraction because we have centimeters cubed that needs to cancel. And then if we kind of plug all this in, the density of water at this temperature is 997.2 kilograms per meter cubed. Okay, so we can basically plug all that in. This pressure, we're given it in 100 kilopascals, but we need to use the SI unit, the pascal. So we got to multiply it by 1,000. And then this is our density in SI units. This is our gravitational constant. And then this, we work through the math, it's 10.22 meters. So this means that if we had a water barometer just kind of out in the air, it would be over 10 meters high. Whoa! That's how strong atmospheric pressure is. Just a thing to note that we could have used kilopascals in the numerator as long as we used liters rather than meters cubed. It's a little tip. If you don't remember that, that's fine, but it's a bit of a shortcut that some students like to use. Okay, another super popular exam problem is this. We have the height of a mercury barometer at 25 degrees Celsius. It's say 813 millimeters. So this is our mercury barometer. We want to know what the height of the water barometer would be. So basically the height of the column if we were to switch the fluid from mercury to water. Since they're both under the same pressure, the pressure of the mercury has to be equal to the pressure of the water. And if we use our new favorite equation, P equals rho hg, we substitute that for each one. This is the mercury side, the density of mercury times the height of mercury times the gravitational constant equals the density of water times the height of water times g. And check this out, g cancels out, and if we solve for the height of water, which is what we want, divide both sides by the density of water, we have this ratio, the density of mercury to water times the height of mercury.
Aha!
Now, at this point, we need to plug things in. We need to know what the density of mercury and water is at 25 degrees Celsius, because it varies based on the temperature. I looked up in the engineering toolbox you can see online, the density of water at 25 degrees Celsius is 0.997-ish grams per centimeters cubed. So we'll kind of plug that in there. And then if we look at the data tables, this is from the NIST website, the density of mercury at 25 degrees Celsius is about 13.5336 grams per centimeters cubed. So we can plug that into here. And at this point, we can just use grams per centimeters cubed because they cancel out. And this ratio, this fraction, becomes 13.57. It's unitless. The height of the mercury column is given. It's 813 millimeters. So if we plug all this in, this gives us a height of about 11,000 millimeters if the barometer was water. How high is that? Well, it's about 11 meters tall. So pretty high if it was water. While a barometer is useful in measuring atmospheric pressure, a manometer is useful in measuring other stuff, like gases and things like that. And there's two types. This is a closed end type. The end right here is closed to the atmosphere. So the pressure of the gas pushes on the fluid, say mercury, and that pushes it up. And the pressure of the gas equals the hydrostatic pressure of the mercury. It's the pressure due to the force of gravity that's pulling down on the mercury, which is H rho, which is the density times g. If you derive this, you can check that out, as opposed to the open end type. Now, if the gas has a pressure that's less than atmospheric pressure, what happens is that atmospheric pressure wins, it pushes down, and it pushes this column up such that the pressure of the gas plus the pressure due to mercury, or whatever the fluid is, equals atmospheric pressure. Now, let's plug some numbers in to solve for the pressure of the gas. The pressure of mercury is equal to rho GH. You can check out my derivation if you need to see that. So at this point, we can just plug everything in. This is our atmospheric pressure, 1.010 atm. That's what we're given. And it's useful to have everything all in the same unit. So I'm going to convert everything into SI units. And the conversion for that for pressure is 101,325 pascals is equal to 1 atm. In this way, atm cancels out. And for the other one, we want it in pascals, right? And a pascal is a kilogram per meter second squared. So we got to be in SI units for the second term. Well, the density of mercury at this temperature, I guess it's not given, but just in this example, this is the density, is in kilograms per meters cubed times G times the height, and this is the height in meters, which is very important. So now that we're in kilograms, meters, and seconds and all that, that works out to be pascals. So we have this many pascals minus, or 15,604 pascals. The first term is to 4 sig figs because our atmospheric pressure is significant to the third decimal place. So we have 4 sig figs here. And then in the other one, we have 4 sig figs for the height, so we have 4 sig figs there. Now if we subtract these two together, we have 86,730 pascals, which is actually 3 sig figs because we lose a leading place value right here when we subtract these two together.